Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. We're continuing our Trigon Tuesday looking at the mathematics of Al-Biruni, who measured the radius of the Earth in about 1000 AD. Now, in our first episode on this, we figured out how high the mountain was. Now let's go ahead and complete his method for measuring the radius of the Earth. Now, as you may recall, the way Al-Biruni did this was he measured the angle of drop to the horizon from the top of a mountain. Now, he didn't know the distance to the horizon. He did know the height of the mountain right here because we derived that using the tangent function in our last episode. Now we're going to figure out how to calculate the radius. So let's cue up the music and get going. Now, before we start throwing a lot of numbers in here, let's just go ahead and figure out what we're doing. Now, I've drawn the Earth up on the board. The height of the mountain is h, and we've determined that with the formula that we derived during our last episode. Now, what he's doing is he's up here at the top of the mountain, and he's looking down at the horizon, and he's very accurately measuring this angle right here. And that is an angle from the horizontal at his position. Now, there's a couple of things that are interesting here. First of all, this is a right angle. So, this angle is 90 degrees minus that angle. This is also a right angle. So, what we have is that this angle is also that angle. And that's the key part of this method. Now, I wanted to show you the basic overview of the method, but let's go ahead and make that a little bit smaller and go through the mathematics. Now, like most mathematics, the relationship is very easy to state. Cosine of alpha, which is this angle right here, is the radius, which is the adjacent, over the hypotenuse, which is the radius plus the height of the mountain. Pretty straightforward. We can rearrange that so that cosine alpha times the radius plus the height equals the radius of the Earth. So what we want to do to solve this is we want to get all the r's on one side of the equation and then solve for it. Now, let's go ahead and start from here. Now, cosine alpha times r plus h equals cosine alpha times r plus cosine alpha times h. And all that equals the radius of the Earth. We haven't changed anything. Now, this one is actually a little bit simpler to solve than our last one was. Now, remember, we want all the r terms on one side. So what we're going to do is we're going to say cosine alpha h equals r minus r times the cosine of alpha. So basically we brought that term and brought it down to here. Now, as you recall from our last episode, we can factor this. So let's go ahead and do that again. Cosine alpha h equals r times 1 minus cosine alpha. Now the solution to this then will be quite simple. So let's go ahead and write the solution to this together. So cosine alpha h divided by this term right here, 1 minus cosine alpha equals r. And that's really all there is to it. It's a very straightforward algebraic expression. Now, let's go ahead and put some real numbers in with this. If we have an observer height of 500 feet, the drop to the horizon will be 0.361 degrees. The cosine of that angle is 0.99998. Now, if we plug that into our formula here, we come up with a radius of the Earth of 4734 miles. Now, why is it higher than the actual radius of 3959 miles? Well, that's because of refraction. Now, as you recall, a standard adjustment for refraction, which is measured independently, is 7 over 6r. Now, if you divide by 6 over 7, you end up with 4,058 miles and some change. That's within 100 miles or so of the actual radius of the Earth. This isn't a bad method. Now, when Al-Biruni did his measurement, he was using an astrolabe. And an astrolabe is accurate only to about 1/10 of a degree. So the fact that he got as close as he did with the equipment that he had was pretty remarkable. The other thing is he didn't have any idea of the effects of refraction. So Al-Biruni's Earth was probably about 20% larger than our actual Earth right now. Now, the higher you go with this, the less refraction has an effect. And this number will start going down towards the actual radius of the Earth by the time you get up to the level of the ISS, for example. Refraction is pretty much non-existent by the time you're 200 miles above the surface. Now let's take a moment and talk about the effects of refraction on the horizon and how much of a building would be visible at a distance. Now, if we're up atop a mountain right here, and we look past the curve of the Earth to a building in the distance, and we see this much of the building right here. All of this part of the building is hidden. That's with no effects of refraction. And this point right here would be called the geometric horizon. Now, with refraction, you get a bending of light. And as a result, this building appears to be elevated a little bit, because as we look out, our eye will follow this path of light. And that building will appear to be higher, when in reality what's happening is the light itself is bending downward. Now notice that the light doesn't hit the surface of the Earth until here. That's the apparent horizon. So geometry determines where the geometric horizon is, and refraction makes that horizon go further out. So the geometric horizon, for all intents and purposes, is the minimum horizon based on a sphere of a certain radius. The apparent horizon is extended past that due to refraction. Since there is so much confusion about what refraction does and doesn't do on the Earth, let me go ahead and explain it in a slightly different way. So here we have the Earth. Here's the center. And the Earth's radius is going to be 1, 2, 3, 4, 5, 6 units, okay? The effect of standard refraction is to increase that by a factor of 7 over 6. So in other words, we're going to go up an extra one. Essentially, what refraction does is it makes the Earth appear a little larger than it actually is. Now, as you recall, the radius of the Earth is 3959. That's the true radius of the Earth. However, this refraction makes the Earth look as though it's about 4,700. And if you want to do the ratio of the two, I've found it's generally about 1.22. It appears to be about 1.22 times the size it normally would. So I hope that cleared a couple of things up and we had a little fun working with the equations. Now in our next episode, we're going to talk about the curve calculator. And that's going to use something called the Pythagorean theorem. So until then, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. Make sure you hit that little like and subscribe button down there in the corner, because I'd really like to have you on Team Bob. So until we meet again, take care and stay healthy, folks.
This rabbit hole's too deep. soar above the science sky, above the science sky.